Welcome back. In this video, we will look at data arrays, which are multidimensional collections of numbers. Real-world data is often captured and manipulated as arrays, and they serve as efficient containers to hold and manipulate data in a way that is computationally very fast. I wanted to cover arrays first before we got to data frames because arrays are foundational for most of analytics, particularly those aspects that use machine learning, deep learning, and more advanced techniques. We will cover basic operations on multidimensional data, and this is something we already covered at a high level during the video on exploratory data analysis. So let us get started. I will share my screen while we work through some code on a Jupyter notebook that you can download. If you are watching this video, I will encourage you to open the notebook on your computer and run the code yourself. You should pause the video from time to time and run the code yourself and make sure that you understand why you get the output that you do. With that, let's get started and I will share my screen. So this is the new Jupyter notebook that you can download from the course website. And the first couple of cells are just marked down text that explain what we are trying to do. And I'll run through those, and we will do a library import. We will import NumPy, which is the main library for managing arrays. And that, in fact, is the only library that we will need to import, at least for the time being. We can create a one-dimensional array using NumPy, using their random number generator. It's NumPy random. And randn is essentially telling the machine to create random numbers based on the random normal distribution. And we want it to give us 4 numbers. So we run this and we get 4 random numbers. Notice that every time we run this cell, we will get a different set of random numbers, which means that the numbers that I get on screen right now will be different from the ones that you are going to get. If you want to change that behavior and if you want your code to be reproducible so that everyone who runs your code gets the same answer, you can set the random seed. And you can set the random seed using the command np random seed. And you can put in any number here, 5, 10, 1, 0. Here I put in 1, 2, 3 for no real good reason, but it can be just any number. And as long as the same seed is set by somebody else, they will get the same results that you do. For the moment, we will not bother with that. I just wanted you to know how to get the same results every time if this is something you're trying to show to someone else. So in this cell, we run and we create a data array which has 2 rows and 3 columns. So the shape of this array is 2, 3. 2 stands for the number of rows and 3 is the number of columns. We can create multi-dimensional arrays. In fact, next we will create a 3-dimensional array. Note that this time, instead of random normal variables, random normal numbers, we are going to create an array with random integers. And you can do that through the randint function, which is also part of nprandom. For randint, we have to specify the low and high. We want our integers to be between 1 and 5. And we want a 3-dimensional array, which should be 2, 3, and 4. Now, think of the dimensions, and I want you to pay some attention to the way the dimensions are structured. So the last two axes, as these are called, these are still the rows and columns. So you get 2 sets of 3 by 4 matrix type elements, and that's what the 2, 3, 4 stands for. You can get the shape of any array by using the shape attribute. So whatever the name of the variable is that contains the array, dot shape is going to give you the shape of the array. And let's run this cell. So we have an array with the shape 2, 3, 4, and as you can see, we have this is the array that was generated. So let's just dissect this for a minute. How does this relate to the 2, 3, and 4 that we talked about? So this is 3, this is 4, and there is a 2 here. So how do we understand these? What this means is that 3 is the number of rows, 4 is the number of columns. So we will get uh, 3 by 4, we'll get a sort of a matrix of 3 by 4, which is what this is. So this, as you can see, has 3 rows and it has 4 columns. So these are the 3 rows, and then there are 4 columns. 1, 2, 3, and 4. And this is so messy. Let me just get rid of the ink. So this explains the 3 by 4 part of the shape of the vector. And then this 2 means that there are 2 of these 3 by 4 matrices. So which is exactly what we see. We have one here. Oops, sorry about that. We have one here and another one here. So there are 2 of these. That's what this means. Now the shape of this array is 2, 3, 4, and often we read these as access. So access 0, as you know, in Python the numbering starts from 0. So access 0 refers to the 2. Axis 1 refers to the number of rows, which is this 3, and 4 is the number of columns, which is the last dimension, and it is axis equal to 2. Again, we can create another three-dimensional array, but this time we use the random normal function and we get floats, which is another name for numbers that have decimal digits. The way these multi-dimensional arrays are represented on screen are through enclosing the numbers with the square brackets, which you see here. So the start and the close of these square brackets indicates the beginning and end of each of the different elements of your array's shape. So I will ask you to spend a minute trying to internalize and look at this and think about it. Um, and again, as I mentioned, analytics is not a spectator sport. You have to run it yourself to be able to understand it well. Now let's add another dimension. Let's make it a four-dimensional thing, because up to 3 dimensions we can visualize it in our head. What this effectively represents is a data cube. These two matrices of rows and columns, they're basically stacked one behind another, and we can think of it as a three-dimensional cube. But we can also create uh, arrays that have many more dimensions than 3. So here is a 4-dimensional array. And again, you can interpret it in the same way. You have a matrix of 2 by 4, then there are 3 of those matrices, and then 2 of the structures that are represented by the 3, 2, and 4. You can check the type, the data type of the variable that we just created by using the function type. Uh, Also, if you happen to have your data in a list, you can easily convert it into an array. For example, here we have a list which contains numbers from 0 to 11. We can now convert this into an array like so here. And as we can see, this is a one-dimensional array, and we can infer that from the number of square brackets. So there is only one square bracket here. So this is a one-dimensional array. We can convert this into a multi-dimensional array. So for example, if we want to convert it into a two-dimensional array with dimensions 3, 4, we can do so by changing the shape of the array as we do here, and we get this result. It rearranges the numbers so that the array becomes in the shape 3, 4. We can also create uh, arrays of zeros. For example, here is a array with all entries equal to 0. In the same way, we can also create an array from a range. So here is a one-dimensional array from a range, very similar to the example before. We can reshape into the shape 3, comma 4. There are two ways, as you can see, we can reshape an array and change its shape into something else. One was the dot shape attribute that we were able to assign a new value to. And then we can also use the dot reshape command, and we can change its shape either way. It gives us the same results. When we reshape an array, we must make sure that the number of elements available is able to fit the new shape. So we can also convert the 3 comma 4 array into a 3 comma 2 comma 2 shape, and this is what we get then. We can also create an array of ones, just like we created an array of zeros. Similarly, we can create an identity matrix where all entries are zero except the diagonal, which is one, by using np.i. NumPy has a large number of functions that make lives very easy for a lot of the work that we have to do. We can also create an empty um, array which shows a zero, but actually is slightly different from a zero matrix. We can also summarize data along an axis. This is often a common operation. And what this means is that we may want to sum our data along the rows or the columns, and we can do so quite easily. We may like to calculate the mean, the median, the standard deviation, etc. So here we have an array, and we want to sum it up along the along the row axis. The row axis is the zeroth axis, which is the first one for this particular type of array. And again, what this means is, what I want to be able to see is be able to see the sum of these two, the sum of these two, and the sum of these two. And I can do so quite easily by using the sum function and specifying the axis equal to 0. I can do the same thing and sum things for this array along axis equal to 1, and I will get two numbers in return, which is the summation along the columns here, because axis is equal to 1. This can get a little bit confusing as to which axis is being summed up, and one way to think about it is that the axis that you specify is the one that will disappear. That's the one that will get summed up or will have its mean calculated, or minimum or maximum or standard deviation. So all of these functions you can use instead of sum in order to calculate the averages or whatever operation you wish to perform. One other important thing I wanted to mention was how to subset arrays. Sometimes you may have a large array and you only need certain rows, certain columns, or certain cells at the intersection of a particular row or column. And that is accomplished using subsetting. Subsetting is a fairly complex field. There are a lot of different variations, nuances, but I'm going to cover the main things here. And generally, what I'm going to cover suffices for pretty much most use cases, even though in some cases more elegant solutions are available. Here, when you are subsetting, you generally specify a start value, which is a number, and a finish value separated by a colon. The start element is included in the result, but the finish number is excluded. So if you have something like 1 colon 3, it means include the first one, include the second one, because it lies between 1 and 3, but not 3. So 3 will not be included. And expressing a colon for a particular dimension means you include everything. So you have to provide the start finish for every one of the dimensions of an array in order to see the particular subset you are interested in. So here we create an array, and this is again a randomly generated array, as you can see. And if I want to see the first two rows and the first two columns, this is how I will do it. And this is exactly, so you can see that by specifying 0 to 2 and 0 to 2, it means take the 0th row and the first row, which means take these two, and then the same way for the columns, and this is what I get as my answer when I do this kind of subsetting. There are other variations that you can apply to subsetting. So for example, I want to see all the rows but only the first two columns, and this is what I do here in this cell. In the same way, I can just look at everything in the first two rows, but and all the columns. So I don't even specify the columns, which means everything gets included. Sometimes you may need to make a copy of a slice, and you can do that by doing dot copy. And this kind of subsetting, which I have just described, for example, this is sort of the long form way. This normally works and is for most use cases and is easy to understand. There are other ways of subsetting that are more concise, and you may come across those in the future. But for the moment, we are going to stick with this long form slicing. So here we take one more example. We create a random array of 4 dimensions, and this is what it looks like. And we check its shape. It's 3, 4, 2, and 5, exactly what we specified. But we also then do a subsetting, which means we say for the first dimension, take the very first element and then show me the shape of that. So in our example, it takes the first one of these sets here, of the 3 sets. It takes this and gives us the shape of just this part of the array. And this subset is a 3-dimensional array, as we can make out from the 3 square brackets that enclose this. So, and we get to see that the shape of the very first element is 4, 2, and 5, which is the same as here. So again, a little bit of a nuance, but it is important that you get a feel for how arrays are shaped, because when we come to images, videos, all other kinds of data, then arrays, an understanding of arrays and how they are structured is important. Similarly, we can do this. There are some more examples of slicing arrays. You can pick selected rows and columns. So for example, we create another array using random numbers. We select the first row, we select the fourth row. We can select both the first and the fourth row together. And we can also select the first and the fourth column, but with all the rows. And this is how you do that. Uh, we can also select a subset of named rows and columns. And here is another example. So again, these are things you should try and match with your intuition to make sure you're understanding what is going on. Finally, I just wanted to close with an explanation of how array operations work. All mathematics on arrays is performed element-wise. And if you multiply an array with a scalar, then each element in the array will be multiplied with that or added or whatever the case may be. So let's look at our array 1 again. This is our array 1. If I were to add 4 to this array, then every element will have 4 added to it. Let's create a new array, an array 2, and this is another random array. And I could perform a comparison of, compare array 1 to array 2. And I want to check if array 1 is greater than array 2. And this operation will also be performed element-wise. So it'll look for is 4 greater than 47 and so on. So it's going to check that, and it will give me the results in the form of booleans. So some are trues and some are false, as I would expect. Similarly, again, I can, it's another example of the same Boolean comparison. I can add 2. This is again a repeat of the previous example. Uh, if I do a summation of a particular array without specifying the axis, it will sum up all the elements of the array. So it gives me a total of all the elements in that array. And again, we have already seen NP sum, which is summation along a particular axis. We can also sort the values in an array using NP sort. So for example, let's define an array which has only four elements, 20, 10, 30, and 0. We sort it, and again, in a very predictable way, it sorts it. We can do a descending sort, which is really just the same sort as before, but with this special sort of extra thing added to the end. What this does is that wherever you are in an array, putting this reverses the order of all the elements in the array. So we really just do an ascending sort, and then we reverse the order of all the entries, and that gives us a descending sort. Similarly, we also have argsort. Say, for example, this is our same array, the 20, 10, 30, and 10, and we can find out the indices of the sorted value. So instead of actually getting the values, it tells us that in the first position is the third value, uh, which is 30. Oh, sorry, which is 0, because this is 0, this is 1, this is 2, this is 3. So it gives us um, the sort. Arc sort is generally useful when you're trying to find a particular uh, the location of the minimum or the maximum value in an array. You also have the argmin and argmax functions. You can use argsort to perform the same kind of sort as before. And again, this is pretty simple. Next, finally, I just wanted to mention distances and angles between vectors. You can calculate the Euclidean distance between vectors using linear algebra, a linear algebra function called norm, and we have an example of this. We will be covering distances more later on in the chapter before we get to machine learning. So hold on for that. But for those who are interested, just be aware that there are functions available to calculate the distance between two vectors. And for text analytics, we sometimes have to calculate the angle between two vectors to understand the similarity between two pieces of text. We can do that again, we can do that using some more vector math, which is explained here. Again, we are going to cover this later again, but I just wanted folks to be aware that when you have two arrays, you can calculate the angle between them. We generally convert the angle into the cosine in order to find out cosine similarity or the cosine distance. Another thing I wanted to mention was matrices. Matrices are a special case of arrays. A matrix is a two-dimensional array. And really, the only real difference between a matrix and array is the data type. And also, you can calculate an inverse of a matrix, but you cannot do that for an array. All other operations are pretty similar. You can see some examples of code that applies to matrices here, and I'm not going to go through that for the reason that it's not something we will be using a great deal going forward, but just something to be aware of. Um, and with that, we end this lesson. Thank you for listening, and see you in the next lecture.